Hello everyone, I hope you guys are doing extremely well. Today we are going to discuss an important problem in our binary search tree series. The problem name is kth smallest element in a BST. So let us understand the problem description first. So we are given the root node of a binary search tree and we are given an integer k. Now we want to return the kth smallest element and k will be one index. So we want to return the kth smallest element in the tree. So problem statement is pretty clear, but let us take an example to understand it more clearly. Let us say we are given the root node of the binary search tree as node 35. The left child of node 35 is node 25 and the right child is node 45. Now for node 25, let us say the left child is node 15 and the right child is node 30. Now for node 15, the left child is null and the right child is also null. For node 30, the left child is node 28 and the right child is node 32. For node 45, the left child is node 55. The left child is null and the right child is node 55. Now let us say we are given k as 2. So we want to find the second smallest element in this binary search tree. So what is the first smallest element? The first smallest element is nothing but node 15. What is the second smallest element? The second smallest element is nothing but node 25. So what will be our answer? Our answer will be nothing but this node 25. So if k is equal to 2, our answer is nothing but node 25. Let us say if k is equal to 5. So for k is equal to 5, what will be our answer? So the first smallest is node 15, the second smallest is node 25, the third smallest node 28, the fourth smallest node 30, the fifth smallest node 32. So our answer will be node 32. Okay. So we want to find the kth smallest element in this binary search tree. Now I want to tell you one more constraint here, that k will always be less than equal to n, where n is the number of nodes present in this binary search tree. I hope the problem statement made sense to you guys. Now let us understand how we can solve this problem. So let us take an example to solve this problem. Let us say we are given the root node of the binary search tree as node 77. Now the left child of node 77 is, let's say, node 67 and the right child is node 87. Now the left child of node 67 is, let's say, node 57 and the right child is node 70. Now for node 87, the left child is null and the right child is node 97. We want to find the third smallest element in this binary search. So how can we do that? So what we can do any of the traversals of the binary search tree. This is the brute force approach that I'm telling. The brute force approach is we can do any of the traversals that we want to do. Let us say we are doing a level order traversal. So what is a level order traversal? I have already explained you a level order traversal in my binary tree series. So please look at that video. So level order traversal of this will be firstly the first level, that is this level, first level, then the second level, and at the end the last level, that is the third level. Okay, so what will be the nodes? The nodes are 77, then 67, then 87, and then we have 57, 70 and 97. Now once we have traversed the binary search tree in any order, what we can do, we can just perform a sorting of this array. So after sorting, what will happen? The array will look like 57, 67, 70, 77, 87 and then 97. Now we want to find the third smallest element, so we need to go to the second index. Why second index? Because k is first 1 based indexing and in our array it will always be 0 based indexing. So we want to find k minus 1th element in our array. So that element will be nothing but 70. So in this case our third smallest element is nothing but node 70. So we are simply going to return node 70 as our answer. So this is the basic brute force approach. So what is the time complexity? The time complexity is simple. It is big O of n to traverse the binary tree, and after that we are performing a sorting operation. So sorting is going to take us n log n extra. So the overall time complexity will be big O of n log n. Talking about the space complexity, we are creating an extra space for this array, so the space complexity will also be big O of n. Can we do something better? Can we do something better? Yes, we can. There is a property of binary search tree. If we perform the in-order traversal of binary search tree, it is going to give us a sorted array. Remember, I told you. So what we are going to do, we are going to do a in-order traversal. So let us understand that. So let us say we are given the root node of the binary search tree as node 35. Okay, the left child is, let's say, node 16, and the right child is, let's say, node 40. Now for node 16, let us say the left child is node 6 and the right child is node 20. Now for node 40, the left child is null and the right child is node 60. Now for node 60, let us say the left child is node 55 and the right child is node 65. Now we want to find the seventh smallest element in this binary search. So how can we do that? So what we are going to do, we are going to do an in-order traversal of the binary search tree. So how do we do in-order traversal? Firstly, we process the left subtree. I have already told you in-order traversal in my binary tree series, so do look at that video. Then after we process the node, and after that we process the right subtree. So this is what we are going to do. So we are going to start from the root node. For node 35, there is a left subtree, so we'll reach at node 16. Okay, from node 16 again we have a left subtree, so we'll reach at node 6. Now for node 6, there is no left subtree, so now we are going to process the node. So what we are going to do, we are going to add this value of node, this 6, in my in-order array. So this is an in-order array which I have created. Initially it was empty, so I have put this 6 in my in-order array. Now is there any right subtree for node 6? There is no right subtree for node 6, so simply return. Now we reach at node 16. For node 16, we have processed the left subtree. Now we are going to process the node. So how we are going to do that? We are just going to add this value, so 16, in our in-order array. Now is there any right subtree for node 16? Yes, the right subtree of node 16 is node 20, so we'll reach at node 20. Now for node 20, is there any left subtree? No. So now we are processing the node. So what we are going to do, we are going to add this value, so adding this 20 in our in-order array. Now is there any right subtree for node 20? There is no right subtree, so we simply gonna return. Now for node 16, we have processed the left subtree, we have processed the road, we have processed the node, we have processed the right subtree, so we again gonna return. Now for node 35, we have processed the entire left subtree. Now we are gonna process the node, so processing the node, adding the value 35 in our in-order array. Okay, fine. Now is there any right subtree for node 35? Yes, so we are gonna reach on node 40. So for node 40, is there any left subtree? There is no left subtree for node 40. So now we are going to process the node. So we are going to add this value 40 in my in-order array. Fine. Now is there any right subtree for node 40? Yes, the right subtree for node 40 is node 60. So we reach at node 60. Now for node 60, is there any left subtree? Yes, the left subtree of node 60 is node 55. So we'll reach at node 55. Now for node 55, is there any left subtree? No. So now we are going to process the node. So 55 will be added in our in-order array. Now is there any right subtree for node 55? There is no right subtree for node 55. So we simply gonna return. Okay, now for node 60, we have processed the entire left subtree. Now we are going to process the node. So 60 will be added in our in-order array. Okay, now is there any right subtree for node 60? Yes, the right subtree of node 60 is node 65. Okay, so node 65 will be added here. Okay, sorry, node 65. For node 65, there is no left subtree, so now processing the node, and node 65 will be added. Is there any right subtree for node 65? There is no right subtree for node 65, so we simply gonna return. Now for node 60, we have processed the left subtree, we have processed the node, we have processed the right subtree, so we again gonna return. For node 40, we have processed the left subtree, no left subtree, we have processed the node, we have processed the right subtree, so we are again going to return. For node 35, we have processed the left subtree, we have processed the node, we have processed the right subtree, so we are again going to return, and that's it. So in the end, we have our in-order array ready. So we want to find the 7th smallest element, so I need to check the 6th index. So what is our 6th index? So this is 0, 1, 2, 3, 4, 5, 6 and 7. So what will be our answer? Our answer will be nothing but node 60. So we are simply going to return this node 60 as our answer. Now talking about the time complexity of this approach, the time complexity of this approach is big O of n, where n is the number of nodes present in this binary search tree. We are not performing any external sorting. We are already getting a sorted array by performing an in-order traversal. Okay, now talking about the space complexity of this approach, the space complexity of this approach is also big O of n, because we are creating an extra in-order array. This solution is really good, but can we do something better? Do we really need to store all of these values in my in-order array? Can we do something better in terms of space complexity? Yes, we can. So let us understand that solution as well. Okay, Okay, fine. So I have told you two solutions. Firstly, the brute force solution. Secondly, the optimal, the better solution. And now we are going to understand the optimal approach. What is the optimal approach to solve this problem? So let's do that. Okay. So now consider the root of the binary search tree as node 33. Now the left child of node 33 is node 23 and the right child is node 43. Now for node 23, the left child is, let's say, node 13 and the right child is node 30. Now for node 43, let us say the left child is node 36 and the right child is node 47. Now for node 13, the left child and the right child is null. For node 30, the left child is, let's say, node 27 and the right child is node 31. Okay, the left and the right child for node 36 is null. For node 47, the left and the right child is null. So we want to find the, let's say, the sixth smallest element. Okay, sixth smallest element. So what we can do, we firstly we need to initialize an answer variable. Initially answer variable will be set as null. In the end, our answer variable is going to tell us the kth smallest node. So what we are going to do, we are going to do an Inorder Traversal, and at every time we are going to process the node, we are going to decrement our k variable. So let me explain you what do I mean by this. So we are going to start from the root node, from node 33. Now what was the first thing? First thing to process the left subtree, then to process the node, and then to process the right subtree. So start from node 33. Is there any left subtree? Yes, the left subtree of node 33 is node 23. So our recursion will reach at node 23 now. Now for node 23, again, is there any left subtree? Yes, the left subtree is node 13. So our recursion will reach at node 30. Now for node 13, is there any left subtree? There is no left subtree. So now what we are going to do, we are going to process the node. So how we are going to do that? We are going to decrement k by 1. So decrementing k by 1, it will become 5. Now whenever the value of k will become 0, that node will be our answer. So here k is 5. So we are not going to do anything. We are going to continue our flow. So node 13, is there any right subtree? There is no right subtree. So we simply want to return. Now for node 23, we have processed the left subtree, we have processed the node. Now we'll process the right subtree. So for node 23, the right subtree is node 30. Now there is this one thing that I forgot. For node 23, when we are processing the node, we need to decrement k. So k will become 4. Okay, now k is not 0, so nothing. We don't need to do anything. Now we will reach at node 30. For node 30, is there any left subtree? Yes, the left subtree of node 30 is node 27. So we'll reach at node 27. Now for node 27, is there any left subtree? For node 27, there is no left subtree. So now we are going to process the node. So how we are going to do that? We are going to decrement k by 1. So it will become 3. Right. Now k is not 0. So we are not going to do anything. So is there any right subtree for node 27? No, there is no right subtree for node 27. So we'll reach at node 30. For node 30, we have processed the left subtree. Now we are going to process the node. So how we are going to do that? Decrement k by 1. So it will become 2. K is not 0. So we don't need to do anything. Now is there any right subtree for node 30? Yes, the right subtree is node 31. So our recursion will reach at node 31. For node 31, is there any left subtree? There is no left subtree. So now we are going to process the node. So processing the node, k will be decreased by 1. So it will become 1. Now k is not still 0. So we are not going to do anything. Now is there any right subtree for node 31? There is no right subtree for node 31. So we simply gonna return. Now for node 30, we have processed the left subtree, we have processed the current node, we have processed the right subtree. So we are again going to return. For node 23, we have processed the left subtree, we have processed the right subtree, we have processed the node. We have processed the node, we have processed the right subtree. So we are again going to return. Now for node 33, we have processed the left subtree. Now we are going to process the node. So processing the node, decrement k by 1. So it will become 0. Okay, now k value has become 0. That means this node, this 33 node is our sixth smallest element in this BST. So what we are going to do, we are going to change our answer to this current node, that is 33. And after this, we are not going to continue our flow. From here, we are just going to return. Wherever we will be simply returning from that. Whenever the value of k will become 0, we will be simply returning from there. Okay, now talking about the time complexity of this approach, the time complexity of this approach is big O of k, where k is the value given to us. Now in the worst case it can go up to n, so the time complexity in the worst case will be big O of n, but the space complexity will be constant, because we are not creating any extra in order array which we had created in our previous solution. Okay, so the space complexity is constant. We are not talking about the recursive stack space, we are talking about the auxiliary space. Okay, I hope this approach is clear. So now we are going to convert this logic into the form of code. So let's do that. Okay, so as you can clearly see, I have already declared a function called kth smallest that is taking the root node and k as an argument. Now root node is nothing but an object of class tree node. I have already explained you in previous videos what is class tree node. It is having a constructor that is initializing the value of the node. The left and the right child of any node is by default set as null. Now k is nothing but an integer value. Okay, now what we need to do? Firstly, we need to initialize an answer variable. So since this is a global variable, because I want to change it at any recursive call, so I'm going to initialize it as an array so that I can pass it in my recursive function. And also I'm changing k in the form of an array so that it will keep updating at every point of recursion. And after this I'm going to call a recursive function. So let's name that function as kth smallest and then util. Let us pass the root, the k and the answer, and from this I just need to return answer of 0. Whatever the value will be present at answer of 0 will be my node. Okay, fine. Now what I need to do, I just need to write this function root comma k comma answer. Now what is the first thing that we need to check whether the node that I'm currently on is null or not. So if the node that I'm currently on is null, so if root is none, so from here I just need to do return. I don't need to do anything, simply return. Now what is the second thing? The second thing is if my I need to go in the left subtree. So let us make a call for the left subtree. So kth smallest util root dot left, and then we have k and then we have answer. Fine. Now we are gonna process the node. So how we are processing the node? Decrement the value of k by 1. So k of 0 minus equal to 1. Okay, now if k of 0 has become equal to 0, if k of 0 is equal to 0, so in that case we need to change our answer as simply what? Answer as this current node, so it will be root. Okay, and that's it. And we can after this we need to make a call to the to the right subtree. So kth smallest util root dot right, pass k and then answer. From here I can just say return. Now there is one more thing that I can do to speed up my code. I can just put an if here, that if my k of 0 is equal to 0, in that case don't do any processing, just simply return, because we have already found our answer and that answer is present at answer of 0. Okay, fine. So let's take an example to run our code. Let us say the root node given to us is node 25, the left child is node 15, the right child is node 35. Okay, now the left child of node 15, that is root dot left is node 5. Now we want to find the second smallest element, so k is 2. So let us call our kth smallest function, kth smallest, and pass the root node and the value of k. So if I'm gonna run this program is going to give me an output in the form of an object, that is a tree node object. So let's just check it first. So it is giving me an object. So let us find the value of this object. So it will be dot value because it is a tree node. So let us check the value. What is the value? So the value is nothing but 15. So let's verify our answer as well, that whether 15 is correct or not. As we can clearly see, 5 is the smallest value, then the second smallest value is 15. So our output is pretty correct. Okay, I hope this code made sense to you guys. If you guys still have any queries regarding this problem, please drop your concern in the comment section and I will be more than happy to help you there. Regarding this series, I will be uploading more of the questions in the upcoming week. So keep following us. Until then, keep smiling and keep coding. Thank you.